Hi everyone. In this video, we'll go through mathematical induction related problems taken from miscellaneous exercise in the chapter. We will also look at skew symmetric matrix problems and matrix algebra problems. There are many problems related to mathematical induction. Let's go through. So using principle of mathematical induction, you will have to prove this particular statement. If matrix A is equal to this one, then prove that A to the power n is this one, cos n theta, sin n theta, sin n theta, cos n theta, for all n, for all natural numbers. So n can be 1 till any infinite number. The matrix should be like this. So steps are important. We put first n is equal to 1. Put n is equal to 1. When you put n is equal to 1, it's going to be a to the power 1. A to the power 1. Instead of n, it's going to be 1. So cos theta, sin theta, cos theta. Because everywhere n is going to become 1. Now, this is first step. Second step, you assume for n is equal to k. Instead of n, if I put k, what's going to happen? It's going to be a to the power k, cos k theta, sin k theta, cos k theta. Right? This is what we assume. So we get this as the matrix. Now what we do? We find for, this is first step, second step, third step is put n is equal to k plus 1. Standard steps follow this. There are multiple sums, but standard steps. Take n is equal to k plus 1. Third step. Put n is equal to k plus 1. If you put n is equal to k plus 1, then the matrix will be like this. Instead of just theta, you'll have k plus 1 theta. Right? When you put n is equal to k plus 1. This should be the result. Now, what we will do is, we'll just take a to the power k plus 1. We'll not write this matrix. We will not write this matrix. We have to get this matrix. We'll have to arrive with this matrix. Let this be LHS. LHS. In the LHS, we have a to the power n. Instead of n, we'll put k plus 1 and we'll get a to the power k plus 1. We can write a to the power k plus 1 as a to the power k into a to the power 1, correct? Because you can add the powers and it's going to become k plus 1, correct? Now, what is a to the power k? We have obtained this in the second step. What is a to the power k? Substitute this. You substitute this here. Then a, matrix A, this one. Substitute here, matrix A, and this is a to the power k. Now you use matrix multiplication. When you use matrix multiplication, you get something like this. Here use trigonometric formulas, right? Whenever you have this cos and sin, try to use this trigonometric formulas of cos A plus B, sin A plus B, cos A minus B, sin A minus B. Use this formula. So here you will get cos A cos B minus sin A sin B. What is cos A cos B minus sin A sin B? It's nothing but cos A plus B. Cos A plus B. And instead of A, we have k theta and theta. Cos k theta plus theta. Sin k. Similarly, cos A sin B and cos B sin A is nothing but sin A plus B. Sin A plus B. Instead of A, we have k theta. Instead of B, we have theta. So we get this matrix. Now, if you look at it, take theta outside. K theta plus theta, you can take theta as common. So theta is common. You're left with k plus 1. K plus 1. K plus 1 theta everywhere. Right? Now, if you look at this, this is nothing but the matrix that we wanted. Right? What we wanted, when you substitute k plus 1, we have to get cos k plus 1 theta, cos k plus 1 theta. This is what we wanted. Right? Everywhere we wanted this. We got this. We got this matrix. So, thereby, this is nothing but equal to RHS. You can say LHS is equal to this matrix. Since LHS is equal to RHS, this result is true for n is equal to k plus 1. Thus, by principle of mathematical induction, which means that if you continue this process k plus 1, k plus 2, k plus 3, if you keep on doing this, you are going to get a to the power n is equal to this entire matrix. Here there is an example. Matrix A is given. You have to prove that this particular statement is true, where I is the identity matrix of order 2 and n belongs to natural numbers. So start with step 1, n is equal to 1. In this entire thing, put n is equal to 1. You will get this. You got AI plus BA, right? So you started with AI plus BA and you got it as AI plus BA. Therefore, this condition is true for n is equal to 1 because you're getting LHS is equal to RHS. Assume for n is equal to k, substitute n is equal to k, we'll get this. For n is equal to k plus 1, you're going to get this, right? Based on this condition, what we're supposed to get when n is equal to k plus 1? This is what we have to get. This entire thing we have to get when n is equal to k plus 1. So you start with LHS. LHS is this much, this part, right? Now you split this, split it into k and 1, k into this entire thing with 1, k into 1. Now, what did we get? For k, we got it here. What we had assumed for n is equal to k, we have this expression here. Substitute it here. You substitute this entire thing here. And this you leave it like this. Now you take each of these elements and multiply with this. Right? So when you multiply, you're going to get like this. This list of expressions you're going to get. Right? There is common factor here. These two are similar. Right? A to the power k, b is common. Take this as common outside. So you'll be left with k, and this entire thing is 1, k plus 1. You got this. Then you're left with this. What you'll do is, these are all constants. There is matrix A here. This capital letter A is the matrix. So A is given as this matrix. Substitute that matrix. It's A square. So A into A. You multiply this, you'll get 0 matrix. When you multiply these two matrices, which is A into A, you will get 0 matrix. And when you multiply 0 with any number, it's going to be 0 only, right? 0 matrix is nothing like 0 in our number system. So you're going to get 0. And finally, you have this result, right? Now you notice the RHS. We wanted this. This we wanted. So we got the same thing. So this is equal to RHS. Hence the result is true for all n is equal to n, because the result is true for k plus 1. Let's take another example. If A is equal to this particular matrix, prove that A to the power n is this matrix for all natural numbers. So step 1 for n is equal to 1. Just remember these steps. It's a 3-step approach. First step, put n is equal to 1. A to the power 1 is going to be, substitute in this matrix for n is equal to 1. N is equal to 1. So it's going to be 3 to the power 0 everywhere. 3 to the power 0 is 1. So what did we get? We got matrix A. A to the power 1 is matrix A itself. So this for n is equal to 1, this statement is true. When n is equal to 1, this matrix is true. You get 1, 1, 1. You get this matrix A. Now we'll assume for n is equal to k. Since n is equal to 1 is this, n is equal to k, we will substitute k here. Wherever there is n, we'll substitute k. So you get a to the power k is equal to 3 to the power k minus 1. Right? Now, third step, when n is equal to k plus 1. So instead of n, I put k plus 1. A to the power k plus 1 is equal to k plus 1 minus 1. It's going to be 3 to the power k plus 1 minus 1. Right? Because n is equal to, it's like this. It is 3 to the power n minus 1. I'm going to put n as k plus 1. 3 to the power k plus 1 minus 1. So it's going to be minus 1 plus 1 going to get cancelled. Left with 3 to the power k. Right? 3 to the power k. So basically, if you put n is equal to k plus 1, a to the power k plus 1 should be this. This is the result. This is RHS and this is LHS. Right? So what we will do, we'll take LHS. We'll take only LHS. And that is, LHS is a to the power k plus 1. We'll take this and we'll perform certain operations so that at the end of it, we have to get this RHS. So we'll take LHS here. You can write a to the power k plus 1 as a to the power k into a to the power 1. I mean, this is a very common step. For every sum, we'll have to split it like this. We have to split k plus 1 as k and 1. Right? Now, when you split, we assumed the matrix for a to the power k. What is a to the power k? This is the matrix for a to the power k. Substitute this matrix for a to the power k into A, matrix A. Now you do matrix multiplication. When you do matrix multiplication, you are going to get this one, like this. What is this? This is nothing but RHS. This is equal to RHS. Since LHS is equal to RHS, you took the LHS, you did matrix multiplication, you splitted it, you did the matrix multiplication, and finally you got this matrix, which is same as RHS. Since LHS is equal to RHS, we can say that this result is true for n is equal to k plus 1. Right? Now, if you look at the steps, this result is true for n is equal to 1, for n is equal to k, for n is equal to k plus 1. So, since it is true for all of these three things, for n belonging to natural numbers, a to the power n is this particular matrix. Therefore, a to the power n is equal to this for all n belonging to n. Let's take another example. If A is this particular matrix, prove that a to the power n is equal to this matrix where n is a positive integer, any positive integer. Step 1, for n is equal to 1, n is equal to 1, put n as 1 here. So you get a to the power 1 is equal to, substitute n as 1. So you'll get this matrix. What is this matrix? Same as this matrix, right? Therefore, for n is equal to 1, this condition is correct. This equality is correct when n is equal to 1. Now we assume for n is equal to k. For n is equal to k, a to the power k is equal to, we substitute k instead of n and we get this matrix. Now, third step, here we assumed, here we proved, here we assumed. Now we are going to take another proof for n is equal to k plus 1. So you can write a to the power k plus 1 is equal to, when you substitute in this matrix, you are going to get this. Okay, this is nothing but, we can call it as RHS, or the actual matrix which we want. RHS or matrix 1. We call it as equation 1. Now you start taking LHS. LHS is equal to a to the power k plus 1. We can write this as split. Remember, split and multiply. Split and multiply. A to the power k plus 1 is a to the power k into a to the power 1. What is a to the power k? Whatever we assumed. We assumed and we got this matrix. Substitute it here. Then multiply with matrix A. Right? Now do the matrix multiplication. Right? And you're going to get this value, this matrix. And if you observe, this matrix and this matrix are same. Basically, it is nothing but RHS. So LHS is equal to RHS. Therefore, the result is true. Therefore, result is true for n is equal to k plus 1. Therefore, result is true for n is equal to k plus 1 because LHS is equal to RHS. Therefore, the result is true for all positive integers because it's true for n is equal to 1, n is equal to k, n is equal to k plus 1. We proved all of it. So thereby, it is true for a to the power n also. Right? Thereby, it's true for all integers. So we write therefore e to the power n is equal to this one for all positive integers. Another example here, right, to prove by mathematical induction. If A and B are square matrices of the same order such that AB is equal to BA, then prove by induction that AB to the power n is equal to B to the power n into A. Further, prove that A into B to the power n is equal to A to the power n into B to the power n for all n belonging to natural numbers. So same steps for n is equal to 1. Take this. If you put n as 1, you're going to get AB into A to B. Substitute n as 1, so you're going to get AB is equal to BA. So that is correct. They've already told that AB is equal to BA. They've told that. So the condition is proved for n is equal to 1. Now assume n is equal to k. So you're going to get A into B. Instead of n, it's going to be k. Instead of n, it's going to be k. So you're going to get this. Right? Now we'll go to the second step is done. Third step. First step is done. Second step is done. Third step, for n is equal to k plus 1. For n is equal to k plus 1, it is going to be this particular condition. Instead of n, we put k plus 1. So we're going to get A into B to the power k plus 1 is equal to B into k to the k plus 1 into A. This is what we're going to get. Now we'll take only this LHS part. LHS is equal to this part. We take this, we can split this. Split and multiply. Split it as A into B to the power k into B to the power 1. We can substitute this like this. Right? And now we have A into B here. What is A into B? It is BA. So A into B is BA and we leave B to the power k as is. Now B into B to the power k is B to the power k plus 1. We can write this k and 1. We can add the powers. It's going to be k plus 1 into A. Now if you notice, this is same as this one. Same as the RHS, right? Same. So we have derived it. Therefore, for n is equal to k plus 1, this condition is correct. This condition holds good when n is equal to k plus 1. Therefore, result is true for n is equal to k plus 1. Therefore, result is true for all n belong to natural numbers. Therefore, result is true for all n belonging to natural numbers. That is this result. Now, this is the second part of the problem. Further prove that this particular statement we have to prove for all natural numbers. Same thing we'll start with. We'll take this statement. Okay, take n is equal to 1. Substitute, you will get AB. AB is equal to AB, obviously. AB is AB. Correct? Then we go with second step, which is n is equal to k. Just substitute, you will get this. Then we'll take third step, first step, second step. We'll take the third step, n is equal to k plus 1. When n is equal to k plus 1, what is that we are going to get? We will substitute. This is what we are supposed to get. When n is equal to k plus 1, we are supposed to be getting this one, right? E to the power k plus 1, b to the power k plus 1. Now we take the LHS. We take only the LHS. You split it. You write a into b to the power k, a into b to the power 1. So when you split it, this is going to be, we can write it as a to the power k into b to the power k into a into b. Now, a to the power k and a to a, we can add the powers. It's going to be a to the power k plus 1, b to the power k plus 1. Now, what is this? If you notice this is nothing but the same as RHS. This thing is same as this RHS. So, since LHS is equal to RHS, result is true for all n is equal to k plus 1. Thereby, result is true for all n belonging to n. Now, let's go through multiple examples related to symmetric and skew symmetric matrices. This is one of the example. If A and B are symmetric matrices of the same order, then show that AB is symmetric. If and only if A and B are commute. That is, if AB is equal to BA. Final thing is to show that AB is symmetric. If you have to show AB is symmetric, what is the condition? First condition, if AB is symmetric, AB transpose should be equal to AB, correct? For any matrix to be symmetric, the transpose of it should be same as the matrix. AB transpose should be equal to AB if AB has to be symmetric matrix. Start from here. So, and it's also stated that A and B are symmetric matrices. A and B. If A is a symmetric matrix, then A transpose is equal to A. If B is a symmetric matrix, then B transpose is equal to B. Now, with all these 1, 2, and 3 conditions, we will have to prove that AB is symmetric. Now, you start with AB transpose. You start from here, AB transpose. Then you ensure that you get AB as the final result. Perform a list of operations such that AB transpose becomes AB. So, by transpose property, AB transpose is nothing but B transpose into A transpose. This is a transpose property. AB, the old transpose, can be written as B transpose into A transpose. Then, since B is a symmetric matrix, B transpose is equal to B and A transpose is equal to A. They've already told that A and B are symmetric matrices. So, we substituted B transpose and A transpose as B into A. So, AB transpose is equal to BA. But we need AB transpose is equal to AB, right? But they've told that AB is BA. Only if AB is equal to BA. Only if AB is equal to BA, we can call that AB is a symmetric matrix, because here we have got BA, but what we need is AB. So, if we need AB here, then we'll have to say that BA is equal to AB. Only if this B into A is equal to A into B, then we can say AB transpose is equal to AB, which means AB is a symmetric matrix. So basically, to say that AB is a symmetric matrix, we need to ensure that A into B, the condition should be that A into B is same as B into A. So that is what they're asking us to prove. So that is what we have proved here. Here's another symmetric matrix related problem. If A and B are symmetric matrices, prove that AB minus BA is a skew symmetric matrix. A and B are symmetric means A transpose is equal to A, B transpose is equal to B. And we have to prove AB minus BA is skew symmetric. AB minus BA is skew symmetric means, what is skew symmetric? This is skew symmetric. A transpose is equal to minus A. This is skew, right? So here, instead of A transpose, we have AB minus BA. AB minus BA transpose, we'll have to prove that it is minus AB minus BA. We have to prove this statement. AB minus BA, the whole transpose is equal to minus of AB minus BA. That is nothing but minus of AB minus BA is BA minus AB, right? We'll have to prove this. You start with LHS. That is, you take this transpose, AB minus BA, the whole transpose. Now you split it. Based on the property, you can split this. AB minus BA, the whole transpose is AB transpose plus BA transpose. I can write it like this, correct? I can write it like this. I can split it and write it like this, right? Now, what is AB, the whole transpose by property? AB, the whole transpose is AB transpose is B transpose into A transpose. Reverse B and A, right, in the order. So this is, so you write B transpose is equal into A transpose. Similarly here also, A transpose into B transpose. Reverse the positions. So we will rewrite this. Since B is a symmetric matrix, B transpose is equal to B, A transpose is equal to A. A transpose is going to A, substitute, B transpose is equal to B, and minus is going to be put out. So we got this BA minus AB, which is equal to RHS. So thereby we prove that AB minus BA is a skew symmetric matrix. Another example, show that the matrix B transpose AB is symmetric or skew symmetric. We have to prove B transpose AB is symmetric or skew symmetric based on if A is symmetric or skew symmetric. So what this means is, if you assume that A is a symmetric matrix, then this B transpose AB is symmetric. If you assume that A is skew symmetric, then this B transpose AB is skew symmetric. So based on whatever you take A as, that's going to be the result for B transpose AB. So let's take case by case. Let's take first case. We have to prove B transpose AB as symmetric. If this has to be symmetric, A also has to be symmetric, right? We'll have to prove that if A is symmetric, we have to prove that given A is symmetric, this has to be symmetric. So we take this. Now you take transpose of this. B transpose AB, you take transpose of this. Because ultimately we have to prove transpose of this. What is the condition for it to be symmetric? If B transpose AB has to be symmetric, condition is transpose of this has to be matrix itself. That is A dash is equal to A for symmetric matrix. Instead of A, we put this expression B transpose AB. The whole transpose is equal to B. We'll have to prove this statement. So you take LHS first. LHS is this one. You take this portion. You perform certain operations and you have to get this portion. That is RHS. If you get this portion, that means you can prove that matrix is symmetric. So now you take this by property, by transpose property, a very important property, right? It's used in many problems. By using this transpose property, it's going to be AB transpose is equal to B transpose into A transpose. So you can assume that AB is one group, B is one group. So you will get AB transpose into B double transpose here, because there's already a transpose here. Transpose of that AB transpose, again you can split. AB transpose is B transpose into A transpose, and B double transpose is nothing but B itself. Transpose of transpose is matrix itself, right? So we are going to get this. And one more thing, A transpose is nothing but A, because A is symmetric. They've told that A is symmetric, right? So A transpose is A. So we get this. If you notice, this is same as RHS. Thereby this matrix is symmetric matrix. Therefore B dash AB is symmetric, right? Now we'll take the case 2. In case 2, we'll have to assume that A is skew symmetric matrix and then prove that this entire thing is a skew symmetric matrix. What is the condition for skew symmetric? If this has to be skew symmetric, condition is transpose of this entire thing should be negative of this entire thing, right? So you start with LHS. Take this as the LHS, right? Now using the transpose property, take this as one group and this is one group, right? So it's going to be like this. So AB transpose into B double transpose, because already a transpose here, and again you further split this, B transpose into A transpose. B double transpose is B itself, and since A is a skew symmetric matrix, the condition is A transpose is equal to minus of A. This is a condition. So instead of A transpose, we'll put it as minus A. Now when you rearrange, you're going to get this, which is nothing but the RHS. This shows that B transpose AB is skew symmetric matrix. Now let's take another matrix problem. This is coming from the miscellaneous problem section, right? A manufacturer produces 3 products XYZ which he sells into 2 markets. Annual sales is given. There are 2 markets, market 1 and market 2. Annual sales of 3 products is given. Product X, Y and Z are products, 3 products. And these are the sales numbers, right? Now, what we have to find out, if unit sales prices of XYZ, the unit sales prices of XYZ are this much. Find the total revenue in each market with the help of matrix algebra. So, what is total revenue? This is the annual sales of 3 products. The price of each product is given. So, this annual sales is the number of products being sold. This matrix is about number of products. 10,000 products, 2,000, 18,000 products. All of these products, the number of products sold in a given year in market 1 and market 2 is this particular matrix. And this is the price of each product. Now, if you multiply the price of each product with the total number of products that is sold, then you're going to get total revenue. So, formula for total revenue is this into this. We call this as matrix A and this is matrix B. So matrix A into B is going to be total revenue. So you multiply the matrices and you're going to get this matrix. So you're going to get 46,000 and 53,000. So this is nothing but market 1 and this is market 2. So total revenue in market 1 is 46,000 and market 2 is rupees 53,000. Second part of the problem is, if the unit cost of the above three commodities are 2 rupees, 1 rupees and 50 paisa, unit price, unit cost price. Earlier we saw unit sales price. Now this is cost price, right? You have to find the gross profit. What is the formula for gross profit? Sales price minus cost price. Selling price minus cost price is the profit. Sales price we found out earlier. This is the sales price. Total revenue. That is the sale. This is the price. This is the revenue obtained after selling. So this is the selling price, right? Total revenue obtained after selling. And what is the cost price? Cost price is given like this. Cost price of one product is given here. So you have to find the total cost price. Total cost price is nothing but this matrix, which has the number of products that is being sold into its cost price, will give you the total cost price. So you multiply this matrix, you will get the total cost price. This is the cost price, right? Now to find the gross profit, we'll have to take the selling price, which you got here. This is the selling price, subtracted with, this is the cost price. This is the cost price. This is the selling price, total selling price and total cost price. Subtract this and this is what gives you the profit, gross profit. So profit is 15,000 and 17,000. Another problem is to find the matrix X. We don't know what X is. X is a matrix. We don't know what this matrix X is. They've given two more matrices like this. How do we find matrix X? First of all, how do we know what is the order of this matrix? How many elements does it have? We don't know. How do we find out? The rule, order rule. What is the order rule? You have matrix here, you have matrix here. What is the order of this matrix? It's 2 rows and 3 columns. Order of this matrix is again 2 rows and 3 columns. Both are 2 by 3 matrices, correct? Now, what will be the order of X? How do we find out? Based on the condition, order of this particular matrix X, this matrix is getting multiplied with this. What is the rule for two matrices to be multiplied? So basically, when you multiply this matrix X with this matrix, you're going to get this, right? Now we need to obtain the order of matrix X. Order of this matrix is 2 by 3, order of this matrix 2 by 3. The final order is nothing but this 2, the row count is the row count of first matrix. 3, which is the column count, is the column count of second matrix. This is a rule. If multiplication needs to be allowed, then this rule has to be satisfied, right? When you multiply two matrices, this is going to be the order. The row count should be row count of the first matrix and column count should be column count of the second matrix. That means row count of first matrix is 2, right? So we know the row count. Now how do we know the column count? Now you come to the condition. I know the row count. I don't know the column count. What is the column count? I don't know. But I know the order of this matrix. Since these matrices can be multiplied, I assume that the condition is satisfied that this column count and this row count should be same. That is the condition. This column count and row count should be same if matrix needs to be multiplied. Now here the row count is 2. So therefore the column count also has to be 2 only. So the matrix that we have to obtain is a 2 by 2 matrix. 2 by 2 matrix. We assume the elements of this matrix is A, B, C, D. Right? Now you multiply A, B, C, D with this matrix, equated to this matrix. Right? You solve the equations. Right? Take that A plus 4B. By equality of matrices, A plus 4B is this element. 2A plus 5B is this element. 3A plus 6B is this element. So now take any two expressions, A plus 4B, 2A plus 5B. Right? Equal to minus 7, minus 8. Solve them. A plus 4B is minus 7. 2A plus 5B is minus 8. How do you solve them? I have to find values for A and values for B. So I multiply this entire expression. I multiply this entire expression with 2. Because if I multiply this with 2, 2A and 2A is going to get cancelled. Thereby I can find the value of B. So I'll get B as minus 2. Now once I get B as minus 2, substitute the value of B in this expression and I'll get A. So I have the values for A and B. Similarly, find the values for C and D. For C and D, take this. Take this one and this one, equated to this one and this one. So you get two expressions. C plus 4D is 2, 2C plus 5D is 4. C plus 4D is 2, 2C plus 5D is 4. Right? Now you multiply this. You multiply with this with 2. So 2C you will get, it will get cancelled and you can find the value of D. Then once you get the value of D, substitute in any one of these and get the value of C. So you've got A, B, C, D. So X is equal to nothing but A, B, C, D, which is this matrix. Another example, if A is equal to alpha, beta, gamma minus alpha such that A square is equal to I, then choose the right answer. So A square is equal to identity matrix, right? Find A square, right? Multiply A with matrix A, and it should be equal to identity matrix. Now once you do all this, you will get one matrix which is like this, right? You will get a matrix like this: alpha square plus beta gamma 0 0 and gamma beta plus alpha square. You're going to get this matrix equated to the identity matrix. That is, now you form equations. Alpha square plus beta, you take this equation equated to 1, right? And take this equation equated to 1. That is, alpha square plus beta gamma is equal to 1, and gamma beta plus alpha square is equal to 1. Take both of these expressions. So what you will get? Alpha square plus beta gamma is 1 and this one is 0. So you can take 1 the other side. So it's going to be minus 1 equal to 0. You just rearrange this, take minus as common, right? You rearrange this, you will see that 13C is the right option. 13C is the right option. Here you'll have to take minus as common out so that you can get the right match here. The right match is obtained by taking minus outside. If A is a square matrix such that A square is equal to A, then show that this expression is equal to which one of these? Which one of these options? So just evaluate. I plus A the whole cube, right? You expand this. I plus A the whole cube is I cube plus A cube plus 3A square I plus 3A I square and minus 7A. I cube is nothing but I. A cube, they've told A square is A. A cube is equal to A into A square, correct? A cube is A into A square. A square is equal to A. So A square is equal to A. Substitute. So you get again A square. And what is A square? Again A. Nothing but A cube is A. So instead of A cube, I put A. Again, instead of A square, I put A. I. Anything with I is going to be the matrix itself. So A into I is A. Similarly here, 7A. So 3A plus 3A, 6A, 6A, 7A minus 7A is going to get cancelled. You're left with I. So option C is the right answer. With this, we've come to the end of this particular topic and this particular chapter. Thanks for watching. Hope this video was useful.